I hope the slide is visible to you.
Yes, sir.
Yes, sir.
Yes, sir,
Okay.
it is.
So yesterday we were discussing about different weather station instruments. I think one of the instrument we did not discuss is the thermometer, like which is a pretty standard one. Like you have already must be using a thermometer when you get fever or so. So this weather station thermometer means works in the same principle. Like you have some thermometric fluid. Typically, you take mercury or alcohol. So mercury is used because its boiling temperature is quite high. So it doesn't start to evaporate. So that's why mercury is used, and sometimes alcohol is used because its freezing point is quite low. Okay, so if you're measuring at something in the negative direction, -10, -20 degrees Celsius, so you can use alcohol in that case. Okay, so these two are standard fluids. Those are typically used in atmospheric measurement. And temperature in general, it is a degree of hotness or coldness of the air in that particular time and place. How much air, I mean, how hot it is or how cold it is, that is what you represent using the temperature measurement. And generally this temperature is influenced by various factors, like the latitude of the place, then altitude of the place, as well as the direction of the wind, okay, and wind velocity also, and proximity to the sea level. So that varies the moisture content, and by that the temperature is also affected. Temperature of the air is affected. Okay. Okay, so this already I have discussed the mercury and alcohol, why they are preferred one in the thermometer or thermometer used in the atmospheric measurement. And what are the general operating condition you need to ensure? You need to ensure that the bulb of the thermometer, that is freely accessible to the air, incoming wind or the stagnant wind, it should be freely accessible to the air, and it must be protected by or protected from the radiant heat. Okay, so if there is some additional heat radiation which is directly falling onto the bulb, so it will not give you the correct data. So these two, additionally you need to ensure that the bulb is accessible to the air freely. That means it is not blocked by any other instruments, okay, or any other surrounding is actually free from any kind of blockage, then protected against the radiant heat. So to ensure this, generally a box is used, or otherwise it is called Stevenson screen, like the one I have showed here in this figure. Using this particular screen, you can ensure that the safety of the device is ensured. Additionally, this blockage thing can be also avoided. Okay, so you can see that here you have placed the thermometer. There are additional pressure gauge and other devices are there also. Okay, so these are mostly used in the weather station to make sure that I mean, for the safety of the device is also ensured in this particular box. Okay, so that's all for the weather station instrument. And when we comes to the application of this measured data, like all these data are important to us, including temperature, wind velocity, pressure, humidity, whatever measured data we have discussed, or the instruments we have discussed. So everything is important, but from the aerodynamic perspective, we'll be mostly discussing or dealing with velocity, pressure, and the temperature sometimes. So other parameters are not so, I mean, in this course we will not be going through in detail, like relative humidity. So maybe in one chapter when I discuss about the building aerodynamics, and when I come in particular just to discuss about the comfort of the resident, maybe I will discuss about the humidity content. Otherwise, we are not going to talk about other measured parameter as such, like the rain and snow. Those I will not be covering in this particular course. So okay, so now it will be important for us to see the equation of motion, like everything we try to formulate in terms of some equation. So here we will start with equation of motion of the wind. Okay, so if you means you all know that you can use Newton's second laws of motion, which indicates that the force can be equals to mass time your acceleration. Okay, so using this same principle or the same law, you can actually derive the equation of motion for the air parcel or air molecule in the atmosphere. Okay, so that means the velocity of the air parcel or air molecule, the material derivative of the velocity can be it will be equal to the net force it is experiencing. Okay, so that is what it's a very basic equations to start with. So dB by dt will be equals to summation of all the forces that the air parcel is experiencing. So here B is your particle or the air particle velocity or air parcel velocity. So here when I say about air parcel, it has a standard mass and it has a standard volume. Like let's say the volume of the air parcel is dx, dB and dz. Okay, it's a very elementary volume and infinitesimally small. Okay, so from that perspective you need to understand, and we can write its motion using this Newton's second law. Okay, so when we talk about frame of reference, like this equation is valid like when we derive these forces. Okay, so we have to consider frame of reference, means how this force is actually is coming when we change the frame of reference also. So in a stationary or fixed frame of reference, generally you can say that this force will be your pressure gradient force. Like what are the force possible air, I mean possibly on the air particle we experience. You can think about that is one is the pressure gradient force, the other one is your gravitational force, or in some form it is your buoyancy force, and the third one will be your frictional force. Okay, so these three will be your major forces that an air molecule or particle will be experiencing. Is there any other force, do you think? Okay, so these three will be the major force components that the air molecule will be experiencing in a non-rotating frame of reference or non-rotating Earth. But as you know that the Earth is not stationary, it is rotating on its own axis and around the sun. So there will be two apparent forces that the air molecule will experience. Those are your centrifugal force and the Coriolis force. Okay, so when you change or you need to include this frame of references, on a rotating frame of reference, these two additional forces you need to include. So, and then your governing equation for the air molecule velocity will be changed. Okay, so here it is your total derivative, right? You know about this total derivative dv by dt. It is not the partial derivative, this is the total derivative of the velocity. That means it includes both local and as well as the global acceleration. So this dv by dt is now
what is this Coriolis force?
Yes, I will come to the detail. Coriolis force, it comes because of the rotation of the Earth. Okay, or rotational. I'll have a detailed discussion subsequently. Just wait for that. So we get centrifugal force and the Coriolis force, as I said, due to the rotation of the Earth. Now the total force what you have is pressure gradient force. Then you have GA. It is your gravitational acceleration. Then F is your centrifugal force. sorry, F is your frictional force, C is your centrifugal force, and COF is your Coriolis force. Like the letters I have mentioned here. Okay, like for pressure gradient force is P subscript GF. Similarly, gravitational force G subscript A, friction F. Okay, so the same nomenclature we will be following throughout our discussion. Okay, so the air molecule. So these two forces are differentiated based on based on the experience. Like first three forces are generally called as the real forces. Okay, which actually govern the flow motion or the air particle motion, and the other two forces like centrifugal and the Coriolis forces, which are experienced due to the particular change in the frame of reference. Okay, so that's why they are called as apparent forces. Okay, so they are not there if if it is a stationary frame of reference. Okay, so that's why they are not considered as a real force. Rather, it is considered as apparent force. Okay, someone's mic is on, I guess. Please mute your mic. If we now consider or simplify this equation further by taking this gravitational acceleration and the centrifugal force together, so G will be equal to G plus GA plus C. Okay, so we combine this GA and C and define another gravitational acceleration force, and then we can rewrite this equation in further simplified way. Basically, we are neglecting the effect of the gravity or combining the effect of the gravity with the centrifugal force. Okay, so that thing can be done, like their effects can be combined more or less. So we only have four terms here. Your pressure gradient force, then your gravitational acceleration or the centrifugal acceleration, whatever you name it, and the F is your frictional force, and this is your Coriolis force. Okay, now so this equation is basically in a vector form. Okay, now if you want to write it in its component, it will have on a three-dimensional space, it will have three components like x, y, and g. So excuse me. Okay, I'm sorry. Excuse me. So it will have three components, x, y, and g. Normally, these are the direction nomenclature we follow. X is your east and west direction. So x direction this is, and y is your north-south direction. Okay, and z is your vertical motion, like which will be perpendicular to this plane of the screen. Okay, so that is your z direction. So you can see that this surface of the earth you can consider as a one plane. Okay, xy plane or horizontal plane, and perpendicular to that will be your vertical motion. Okay, so generally subsequently you'll see that we'll be just discussing about this horizontal plane or your xy plane, and most of the discussion in the z direction will not be important to us. Okay, so yeah. Yes.
Combine both gravity and centrifugal force.
Sorry, I did not get it.
Why did we combine both the gravity and the centrifugal force as one component?
Yes, so actually gravity effect will not be so strong when we consider about the air molecule. Okay, so the air molecule itself is very small. So that's why we can either neglect that. Instead of that, we can include it. We can include in one form. Like this G is basically your centrifugal force. Okay, so gravity effect in that is very minimal because the size of the air molecule, you can see that this is quite less. So gravity effect is not so important. Okay, so that's why I combined it so that we don't have to discuss it in a separate way. Okay. So now U, V, and W are the corresponding velocity along X, Y, and Z direction. So X direction is your east and west, so that the velocity will be U. V is along the north-south direction, and W is its vertical component, okay, which is perpendicular to the screen. Now, now let's see about. So this is your actually equation of acceleration, and for a unit mass of the air molecule, this can be also considered as your equation of the force. Okay, if I say m is the air molecule mass and I consider m as 1, so then that will be equal to also, I mean, that equation will be also considered as force equation, like here I have mentioned here. So if you have a unit mass, then force will be equal to acceleration, and this will be also a force. So it will be like, now let's see what are the different type, like the detailed discussion about different forces. So we start with pressure gradient force. So pressure gradient force, it actually by name itself you can see that it is a force which is experienced when there is a pressure gradient observed in the atmosphere. Okay, so now the pressure gradient generally, if I some of you might have seen this type of weather plot. Okay, so some location you will see that there are these solid lines, and there are some lines which are circulating around a point. Okay, so these are generally called as isobars. Okay, so isobars means they have the same pressure. Like these lines are connected through those locations where you have experiencing same pressure. Okay, so these are the isobars. Now, when you move from one isobar to the other, you can see that there is a change in the pressure. Okay, so due to this change in the pressure, or if there is a presence of the pressure gradient, then the air molecule will experience certain forces, like that is quite obvious. It will move from higher pressure to the lower pressure. Okay, so that is what the pressure gradient force is. When there is a pressure gradient present in the atmosphere, so the air molecule will experience this pressure gradient force and move from higher pressure to the lower pressure. Okay, so here I have considered two isobars. The bottom one is your low pressure and the top one is high pressure, and to represent the force on this particular air molecule, which has infinitesimally small volume, dx dy dz, and let's say at this point the unit normal vector is pointing outward, and it is n. Okay, then you can represent how much amount of pressure gradient force this air molecule will experience because of this high and low pressure. So that will be your PGF will be equal to minus 1 by rho dP by dN. This you can derive, right? It is not so difficult from the Taylor's expansion. Considering these two location, like higher pressure and low pressure region, you can find out this will be the net force on this air molecule will be minus 1 by rho dP by dN. Okay, so here rho is your air density and n is your actually the normal direction. Okay, another thing is here I have considered a negative. Why did I do, why did I consider the negative? Because you can see that it is or the air molecule will move from higher pressure to the lower pressure. Okay, so it's in the opposite direction, not low to high. So that's why we need to consider a negative. Okay, so this will also appear when you do the Taylor series expansion between these two location. Okay, so this is your pressure gradient force. Now, again, that pressure gradient force, it can be represented in a three-dimensional form. Like you can see that it will have both x, y, and g direction. So these will be in the component form. Del PGFX, like pressure gradient force along the x direction, minus 1 by rho del P by del X, and similarly you can follow for the y and z direction. Okay, and if you combine these three components into one equation, so it will be this. Okay, so I have written here. So in xy plane, or which will be calling it as a horizontal plane, will be the components will be del p by del x and del p by del y. Okay, so this will be your xy plane or east west north south, that particular plane. And del p by del z will be your k component or vertical motion of the air molecule. Okay, so I think this coordinate system is clear to you, right? This is the coordinate system, x, y. Okay, so this is will be considered as xy plane, and z is your perpendicular to it. Okay,
So here you are using a left hand system, right?
left hand system. Okay, now so this will be the total when you have three components summed together. Now you can see that the horizontal, I mean the pressure gradient can exist in both horizontal as well as in the vertical direction. All right, so horizontal pressure gradient, like for example here I have shown, if you can have three isobars, like the values are mentioned here, this may be in the millibars. Okay, now if I have xy system or xy plane, so along x direction there is no pressure gradient, but along the y direction there will be pressure gradient. Okay, so then the pressure gradient force will be simplified to only y in this type of pressure distribution. Okay, so this is horizontal pressure gradient, so which include your either the partial derivative with respect to x or y. Okay, and when we come to the vertical pressure gradient, which is when you move higher in the atmosphere. Okay, so generally the pressure varies significantly in this case. Okay, with a slight change in the height, there can be very significant change in the pressure, but up to certain altitude. Okay, so generally in the troposphere or up to stratosphere, you can see that the change in the pressure is quite large. Okay, so this is the graph showing the change in the pressure. Then we will see that this actually change in the pressure in vertical direction, you can simply correlate that with your hydrostatic condition. There won't be any acceleration term involved in this. So del p by del z will be can be simply considered as your hydrostatic equation. Like, so if I integrate this will be p will be equal to rho g h. So that just depends on the height of the height of that particular location where we're considering the air molecule from the sea level. Okay, so that will be giving you just the pressure force at that location. Okay, so this is what I have summarized for the vertical and the horizontal pressure gradient. So vertical direction, pressure decreases with the height. A small elevation change at the low level results in a large pressure gradient. Okay, like I have already said, in the lower atmosphere, a small change will result in a higher pressure gradient. In the horizontal direction, the pressure gradient force or pressure gradient is in general is smaller compared to your vertical direction. Okay, so this is the difference when we consider the effect of the pressure gradients in deriving the equation of motion of the wind, the equation what we just saw previously. So you need to bear this magnitude, like we will be doing order of magnitude analysis subsequently. So you can see that the magnitude of vertical pressure gradient force or the pressure gradient will be larger than the horizontal pressure gradient. Okay. All right, so then the next force is your Coriolis force. Okay, I have G4. Okay, so Coriolis force, this one is like I have said, it is an apparent force. It is not a real force. It is actually observed in a rotating frame of reference. Okay, so what is happening is when I have shown here two images. So if you see that this particular person is rotating on a carousel, you can say that it's that guy is sitting on a rotating frame and is trying to throw a ball onto this particular bucket. Okay, but what you can see, the ball is not going directly to the bucket, but it is moving or deflected sideways. Okay, so this deflection is actually appearing because of the Coriolis effect. Okay, so instead of moving in a straight line when you have a rotating frame, the air molecule will also deflect to its left or right based on whether you are in the northern hemisphere or in the southern hemisphere. Okay, so this deflection, it appears because of the rotation of the earth. Okay, so that is what I have mentioned here. So in the southern hemisphere, you will see that the air molecule will be deflected to the left of the observer, and in the northern hemisphere, it will be deflected to the right of the observer. Okay, so the observer may be standing in the equator or in the pole, it doesn't matter. So in the northern hemisphere, it will be always deflected towards the right of the observer, and in the southern hemisphere, it will be towards the left of the observer. Okay, and based on that, we have seen this particular wind pattern or atmospheric circulation. Now, I think that time Akash was asking, I think. So why we see these particular wind directions in certain way? So you can now correlate based on the Coriolis forces. Okay, or the Coriolis effect. Like the wind which is deflected towards the in the northern hemisphere, which is deflected towards the north, you can see that they will be, like I have said, it will move to its right. So you can see that these all blue color lines, they are moving towards its right direction. Okay, now the wind which are coming from the north to equator, they will be deflected again towards its right, so it will be on this direction. Okay, so that's why you see certain wind direction on different latitude or different atmospheric circulation region, which is generally appearing because of the Coriolis effect. Okay, and there are other effects which will also define this curvature of the wind, that we will see that the friction effect is also there and centrifugal effect is also there. Okay, so but mainly due to the Coriolis effect, these curvatures are defined. Okay, so the wind motion is inclined to directed in this fashion. Now, this Coriolis force generally it can be, or it is proportional to your V. V is your relative wind velocity, and phi is your local altitude angle. Okay, so it is also it depends on the mass of the air molecule. So these three things, the Coriolis force is proportional to. Okay, so higher the higher the wind velocity, higher will be the Coriolis force. Okay, so here I have written the governing equation for that. So Coriolis force is equals to 2m v times omega. So here m is your mass of the air molecule, v is your relative wind velocity, and omega is your angular velocity. Okay, so since the earth is rotating, so its angular velocity will be changed as you move in the latitude. Okay, so this is what the equation of the Coriolis force. Okay, so this you might have studied earlier also. So now for a unit mass, I can drop the drop this term, m term. So the equation is further simplified to 2 omega sine phi and v here. Okay, so here you can see that it depends on this latitude angle phi. So latitude angle is 0 on the equator and 90° on the poles. Okay, so due to that, you can see this Coriolis force will be smaller or 0 at equator, and as you move higher, the Coriolis force will be increasing. Okay, so it will be the maximum at the both the poles, north and south poles, and the Coriolis force will be maximum and 0 at the equator. And what is the direction of the Coriolis force? It acts in the perpendicular direction to the relative wind. Okay, so in this case, it will be, if you follow the right hand thumb rule, so it will be perpendicular to this screen. Okay, your laptop or computer screen. Okay, any question? Okay, if no question. Now this Coriolis force, again, it can be resolved in 3 direction. So we will not go to the detailed like you can self-read about it. So along the x direction, the component will be this. Along the y direction, the component will be this, and z direction, the component will be this. Okay, so you so Coriolis force components, you can in the component form, they can be written in this way. Now, if you can substitute the value of the Coriolis force and the pressure gradient force in the governing equation, like this is the equation, and we can simply neglect the frictional force as well as the centrifugal force or the gravitational force together, then the remaining part of the remaining terms are dv by dt will be equals to pgf plus cof, which is your Coriolis force component. Okay. So I think here this should be your sine term. I think that was the mistake here. COFY will be minus 2 omega u sine phi.
Phi is with respect to x.
Yes. So with respect to x, we have to define with the same angle. Okay, like the angle definition cannot be changed. So this will be with respect to x here. Yes. So that is one thing. Maybe when I share the slide, I will change it. So you can see that the term in the simplified form of the equation is like this. Okay. So this is easy to follow. Now what we do, even if the equation what we just saw is simpler, it is simplified, but it is still having few terms, those we can neglect it based on the order of magnitude analysis. Okay, so here we have simplified by neglecting the frictional effect and the centrifugal force, but further simplification is possible if you consider the order of magnitude analysis. So what is the order of magnitude analysis? This is based on what is the maximum or what is the order of the velocity scale, length scale that you observe in the atmosphere. For example, here u and v velocity, horizontal velocity, normally you experience from 10 to 20 meter per second. Okay, in a general condition, not in a storm or cyclonic condition. So in ideal or in a general situation, you get this much. So so here the order can be considered as 10 power 10 raised to 1. Okay, in vertical direction, the velocity magnitude variation is not so large, so it is 1 centimeter per second. So you can same way you can write its order will be 10 raised to minus 2. So length and depth wise, again the length of atmospheric circulation along the the horizontal plane, it can be up to 1,000 kilometers. Okay, so that's why the order can go up to 10 raised to 6. Height or depth wise, you can see that the circulation will not be that large, so maybe up to tens of kilometer. So it is 2 order less than the horizontal length scale. The vertical length scale is slightly less than, not slightly, significantly less than the horizontal length scale. Similarly, in the pressure wise, horizontal pressure, like we have discussed, the vertical pressure variation is larger than the horizontal pressure. So generally their orders are mentioned here. And here L by U, your length scale to the velocity scale, that is also there. Rho, G, and angular velocity. So their orders are also mentioned here. So now what we do, we take this previous equation and substitute the values in terms of their order. Okay, like the one here, you can see that along the x direction, if you substitute for u and t, you can see that L by U is basically t, right, 10 to the power 5, and u is along the u direction horizontal velocity 10 raised to 1. So this simplifies to 10 raised to minus 4. Okay, similarly del p by del x, you can also see that pressure along the horizontal direction 10 raised to 3 along, and x is your length scale, so that can be 10 to the power 6. Okay, so this simplifies to 10 to the minus 3. So in the same way you can follow the other terms. Okay, and you will see that few terms will be significantly larger and or few terms will be significantly smaller compared to the other terms. Okay, so now if you see here the acceleration term on the left hand side is of the order of 10 to the minus 4, pressure gradient term of the order of 10 to the minus 3, then this Coriolis force term. So one you get 10 to the minus 3, the other one due to the Coriolis this force because of the vertical velocity, which is quite small. Okay, so if I take the order of magnitude analysis, then I can simply neglect this term because it is quite small compared to other three terms. Okay. Similarly, if you go to your y direction dv by dt, so here if you perform the order of magnitude analysis, you can see that more or less these three terms have the same order, 10 raised to minus 4, minus 3 and minus 3. Okay, so we cannot neglect any term here. Then if you go to the last equation, which is along the vertical direction, you can see that dv by dt, dw by dt is of the order of 10 to the power minus 7. Okay, and the other terms are means quite larger compared to this. So 10 raised to 1, and the second term is 10 raised to minus 3 and 10 raised to 1. G is your gravitational acceleration here. So here you can see that you can neglect this particular term. Okay, because it's quite small. So from this order of magnitude analysis or scale analysis, sometimes we also name it. So this is what I have summarized. You can see that few terms you can neglect based on the order of magnitude analysis. The acceleration term generally along the horizontal motion, like in XY plane, it cannot be neglected because they are not that small, but along the vertical direction, we can simply neglect the acceleration term. Okay, because you can see that this acceleration term is quite small. Okay, so this can be neglected. So if you neglect that term, then your equation is simplified. Okay, so this is after you perform the order of magnitude analysis, you can see that these are the significant terms which are left out. Here f is your basically your Coriolis parameter, so which is 2 omega sine phi. Okay, so that is your Coriolis parameter which are left out, and du by dt is your acceleration term. This is your pressure gradient along x and y direction, and here we can simply neglect the acceleration term along the vertical direction. dw by dt is 0, and you're left out with this. So if you rewrite this equation, you can get del p by del z will be equals to minus rho g. Okay, so which is basically your hydrostatic equation. Just you have a gravitational effect on it. Okay, so this is what I was telling you. Like we don't have to consider the vertical acceleration because that vertical acceleration term is quite small in compared to the horizontal force or horizontal acceleration. Okay. Now, this is another thing that we experience in when we just consider two force. This is a quite ideal situation. Generally, if you just consider the pressure and Coriolis force, neglecting your centrifugal force as well as your gravitational effect, then we can see that the ideal wind condition, we can say that it's a geostropic wind. Okay, so geostropic wind, it is the wind which occurs when there is exact balance between your pressure gradient force and the Coriolis force, and the other force effects are not there. Okay, so that means no acceleration. Okay, if there is no acceleration, then your isobars will be a straight line. Okay, so this we will see subsequently. Then if there is no other force, like friction force is also not there, no vertical motion, so no pressure change along the vertical direction. Okay, so if we just simply take the horizontal pressure gradient force as well as the Coriolis force, then we can rewrite the equation along your x and y direction, which you can simplify this equation. Since there is no acceleration, this term will be 0, this term will be 0, no gravitational effect, so we are not considering the third equation. So now the remaining equation is like this. Okay, so from this, here you need to substitute your velocity components as Vg. Vg here, it represents the geostropic component of the velocity along v direction or along the y direction, and ug is your geostropic velocity component along the u direction. Okay, so these are the velocity values, geostropic wind velocity. We just consider the pressure gradient force and the Coriolis force. Okay, so yes, there could be some numerical example, maybe not today's class, maybe subsequently we can do like what will be the geostropic velocity. So you just need to take consider the pressure gradient. From that you can very well define your geostropic velocity. Of course, there is another term which is your Coriolis effect. Okay, Coriolis force term, which varies with latitude angle. Okay, so do remember that. Now, so by looking into this equation, you can further say that if there are isobars, okay, in a certain direction, okay, not in the xy direction, if it is in other plane. So if you know that the pressure gradient between the two isobars, and you know the distance between them in the normal direction, then simply you can find out your geostropic wind velocity using this form. Okay. Now this geostropic wind, like what direction it will be flowing. Okay, so whether it will be flowing perpendicular to the isobar or it is going to flow parallel to the isobar. Let's look into that. What direction this geostropic wind will be flowing. Like since there are no other forces, only we have the pressure gradient and the Coriolis force to be investigated, right? So we consider three isobars here, like one is on the higher side and the one intermediate and one is on the lower side. Okay, so these are three isobars. Let's consider. Like we know that when there is a pressure gradient, the force will be from higher to the lower side. So the wind will starts to flow from higher to the lower side. Okay, so along this vertical direction. Now what happens when the wind starts to flow along this direction, higher to lower, what will happen? The Coriolis force will starts into appear. Okay, because we just need to consider these two forces, right? So Coriolis force will be again perpendicular to the wind direction, the direction which on which the wind is flowing, which is in the vertical direction. The Coriolis force will act perpendicular to that, which is FCA. Okay, so now because of these two forces, the resultant wind direction will not be perpendicular. It will be slightly on a different angle. Okay, so let's say that change in the angle is direction 2. Okay, so on this angle now the wind starts to flow. Okay, so but when the wind is flowing along this direction, what is going to happen? Your Coriolis force will be also now adjusted. Okay, because Coriolis force always acts perpendicular to the wind direction. Okay, or the relative wind direction. So here when the relative wind direction is this on this line, so your Coriolis force has to change, and now it is changed to FCB. Okay, so because of that, what will happen? Now the angle between your FCB and P is not the same. It is different than the previous case. So because of that, the resultant force will be some other direction. So now the wind starts to flow something in the direction 3, not in direction 2, because the resultant force will be along direction 3. Okay, so in this similar way, you can see that the wind direction will continue to change until and unless you get a force balance between your Coriolis force and your pressure gradient force. Okay, so then, and this is only possible in this manner, right? because we know that the pressure gradient is acting perpendicular to this isobars, so which is so the pressure gradient force will act along this direction, and if you have a Coriolis force which is acting exactly opposite to it, then they will balance each other. Okay, so in this case the direction of the wind will be perpendicular to this force balance or parallel to the isobars. Okay, so geostropic wind, it flows parallel to the isobars. Okay, any question?
I have a question. Sir,
Yes.
so what will be the direction of Coriolis force? In which plane it will be acting?
It will be acting perpendicular to the
Pressure.
wind velocity here. Yes.
Then, according to the sign conventions, we have taken X and Y. And in which directions it will be Coriolis force?
See, this force balance is possible when these forces are acting along same line. The line of action of the force, if they are not in the same line, it will not be balanced. Okay.
Okay.
So and the plane of the Coriolis force, it will be perpendicular to the wind velocity direction. Okay.
Okay.
And the velocity happens, which is along the direction of the pressure gradient. All right.
Okay, sir.
Any other question? Okay, so geostropic wind, it acts or it flows perpendicular, parallel to the isobars. So that is the takeaway point here. Okay, so I think I will stop here today. We will continue on Monday. So we will continue in this schedule or any other, like I see Friday 10 to 11. I did not find anyone is unavailable. If someone is unavailable, please mention in that Excel sheet so that I mean, accordingly we can decide whether we need to change the Friday morning time to 10 to 11 or we stick to it. Okay. Okay. Stop sharing.
Excuse me, sir. I have a question.
Yes. Yes, Hitesh. Go on.
Sir, in the coordinate system,